Welcome to my first talk about spate irrigation. I thought we would start by seeing what we can learn from the study of past interventions. I think the first thing to learn and remember is that spate irrigation does not follow normal irrigation practice, and many of the normal irrigation design criteria do not apply. Many of the interventions made during the past 40 years to improve traditional spate irrigation schemes have actually made things worse in some respects. Often the poor performance of these interventions is caused by an incomplete understanding of the situation as it applies in spate irrigation. Modernisation may not necessarily mean improvement. It's important to remember that traditional systems have evolved to suit their circumstances. If something hasn't worked, then the farmers will try to change it into something that works better. Changes to infrastructure made by the engineers may be less compatible with the overall situation than the traditional system. Also, water rights may need to be changed, which can be difficult to arrange because of the conflicting interests of different stakeholders. Here's a nice photo of a typical flood. You can see it's lots of nice brown sediment-laden water. Sometimes that sediment can be very big. Here we have an intake very close to the mountains, and the sediment is coming down as boulders, cobbles, gravel, as well as all the smaller stuff. Managing this size of material can be very difficult. Here's another intake further down a river. In this case, we're looking through the head regulator down the main canal, and what you see is the canal is blocked by what looks to be mainly fine sand. One can provide sediment basins to trap the sediment, but unless these are designed to be flushable, which is expensive, then they can be difficult to clean out. Here we have a basin. It just looks like a wide canal because it hasn't been cleaned, and it can only be cleaned when the canal is not flowing at all and the sediment has dried out, because it's necessary to go in with excavators and trucks. This photograph shows a drop structure, but it's almost buried. Here's the canal downstream of the drop structure. It's well filled with sediment. In fact, farmers planted a crop in it. And why has this risen up? It's because the canal is trying to raise itself to create a stable slope sufficient to transport the sediment. The slope as designed is too flat. Now, if fields rise, canals have to rise. And here we have a case of a canal culvert almost buried because of the sediment in the canal. And as the fields rise, the farmers have more and more difficulty getting water onto their fields unless they raise the canal levels. Here we have the farmers using anything they can find to try to raise up the water level in order to divert it onto the field. So, what are the key lessons for sediment? It's important to allow for sediment in the design by, firstly, try to reduce the intake of coarse sediment. Second, then provide adequate canal slopes to pass the fine sediment through to the fields so it doesn't collect in the canals. Then you have to allow for the consequences of rising field levels, which are the canals and eventually the headworks will also need to rise. It's worth noting that traditional spate irrigation systems can accommodate this progressive change in levels. Here we have an aerial photograph and contours from Sheb in Eritrea and illustrates the sort of rise in field levels that can occur. In the centre we have what was an old village site, so it's the original ground level. To the left we have the irrigated fields. Here there is about 7 meters difference in the elevation. 1 meter is attributable to the ground slope, which is about 1% from left to right. So that indicates there's about 6 meters of sediment in this area, and that's been deposited in about 100 years. This is Wadi Laba in Yemen. On the left we have the original desert. On the right we have the fields. And in between is what looks like an embankment if you're standing out in the desert, except you go up it and you discover fields at the top. Now, field level rise is inevitable in spate irrigation, although the rate of rise will depend on the sediment load in the floods. Canals then have to rise in order to continue to supply water to the fields. Otherwise, the time to irrigate gets longer and longer because the flow from the canals to the fields gets less and less. And time will run out before the fields are irrigated. Diversion structures or intakes also need to rise to continue to supply the water to the canals. Trash is another problem that affects most spate irrigation schemes. Here we have an example of the trash screen at an intake. Originally the bars were about 10 centimeters apart and they blocked up very quickly. You can see the problem with the trash. So they've ripped out most of the bars and now it takes a bit longer to block up. Now here's a heavy-duty engineering solution to the trash problem. An enormous trash screen well upstream of the intake and at an angle so that some of the trash at least will tend to go with the flow over the weir, which is on the right of the picture. Now, one option is not to provide trash screens at all, but let the trash go through the intake. This will work a lot of the time, but in this particular photograph, which was taken after an exceptionally large flood, we can see that one of 3 bays on the head regulator is actually blocked by trash, and it starts because one big branch gets trapped across the bay, it cannot go through, and then that starts to trap other material. But under normal medium-sized floods, blockage does not occur. Here we have an intake which uses quite small gates. This photograph is looking from the back side, about 1 meter square. But you can see sluiceway gates here, head regulator gates there. They just all tended to block up. And once the sluiceway gates block with trash, then the sediment can't be flushed through and everything just blocks up. So, what are the lessons for trash? Firstly, it's often overlooked as a possible problem. Next lesson is the floods can carry much trash. The amount of trash is unbelievable at times. Trash, I recommend, should be allowed to move through the system as much as possible because the trash screens tend to block up. It's also prudent to provide some facilities, such as a simple winch, to help remove the trash at the intake. Intake capacity is another problem with many of the modernised spate irrigation schemes. Because bigger intakes and bigger canals cost more money, there is a financial pressure to reduce their cost and therefore their size. However, unless the spate flow can be diverted while it is available, the potential area cannot be irrigated before the flood is over, because the peak part of the flood just goes on downstream. We will see that in many modernised schemes, the farmers have actually reactivated old intakes in order to enhance their diversion capability. Hydrological assumptions. This actually is the root of many of the engineering misassumptions, is the hydrology. Now, the hydrologists do have a difficult time trying to prepare analyses for floods and water resources for spate irrigation because there's usually very little data. But then they sometimes place too much reliance on whatever data that they can obtain without doing appropriate field checks. If in doubt, ask the farmers to describe the floods. One also has to remember that hydrological data is always historical and may not fully represent the present or the future, particularly with climate change as one factor and upstream developments in the catchment. As well, they may both change the amount of water and the size of the floods coming down the wadis. One example here of a hydrological problem is Wadi Laba in Eritrea. This was based on a more detailed analysis for the larger adjacent Wadi Laba catchment, for which there was a better data set. However, the analysis underestimated the likelihood of floods with very short durations and high peak flows. As a result, the engineered structures were built with insufficient capacity. If we look at the Yemeni wadis, we will often see that the diversion structures were designed with relatively low intake capacities because the hydrological data indicated long flood flows and substantial base flow. However, recent data shows that the base flow has reduced, perhaps due to climate change or increased upstream use of the water. As a result, the intakes cannot supply the intended areas. We therefore end up with multiple intakes. We'll see the modernised schemes often use a single intake at the upstream end of the system, with a capacity based on hydrological analysis. At that intake, water was used for sluicing and flushing and is lost to the irrigation. Also, a single upstream intake provides the opportunity for the upstream farmers to take control over the water supply. As a result, in many schemes, downstream farmers have reactivated old intakes in order to get more water. We should also remember that the floods and the coarse material carried by the floods can be very damaging. Here we have some chute blocks in an energy dissipator, and they're looking like very old teeth, gradually worn away. And on the right, if your cover to your reinforcement isn't very thick, then the concrete will be worn away and the reinforcing bars exposed and progressively ripped out. Breaching bunds. These are often used to reduce the size and cost of a weir, because by producing an embankment alongside a weir as an effective extension, you can reduce the weir itself. Breaching bunds are designed to fail during large floods, for example, greater than 10-year probability. But the actual performance of breaching bunds is very dependent on the hydrological assumptions, and if the hydrology is wrong, then either the bunds fail too frequently or the weir is more expensive than it needs to be. Here we have a plan Wadi Laba in Eritrea as it was originally designed. We have a weir on the left side, and then a long breaching band that's more than double the length of the weir crest. And the problem was that breached at least once a year. Here, Wadi Laba in Yemen, we have weir and breaching band. Here they are approximately equal length. In this case, the breaching band has only breached once in about 30 years. Another thing to learn is try to keep the operations simple. Floods usually come at night, and as far as possible, the system needs to be semi-automatic in order that the water can find its way to where it needs to go with the minimal intervention by the farmers and operators. Here we have what is a canal division structure, effectively, with 1, 2, 3, 4, 5, 6, 7, 8 gates. That's a bit of an operational headache. Water rights. I touched on this previously. It's worth remembering that existing spate irrigation schemes have usually established water rights which have developed based on the existing diversion arrangements. Now, if we improve the structures, we will change the access of farmers to water, usually to the benefit of the upstream farmers. And therefore, it's recommended that if there are going to be implications on access to water, that water rights should be revised and agreed before any construction is commenced. Because once the structures are built, the upstream farmers will probably not agree to any changes. It's also worth remembering that where government goes in and builds something, it tends to increase the beneficiary dependency. Because the farmers look on government planned and funded infrastructure as government responsibility to operate and maintain. And usually government hasn't got the money for that. So emphasis is now on returning operation and maintenance back to the beneficiaries, or for the schemes that have never been modernised, strengthening the existing beneficiary organisations as part of the scheme improvements. It's important to involve beneficiaries in the planning of any improvements to spate irrigation. Previously, modernisation tended to use a top-down approach in which planners and engineers built what they thought was best, and consultation was a matter of telling the farmers what was going to happen. Often there was no benefit to many farmers, and some were left worse off. And because the farmers hadn't been party to the decision-making, they had no motivation to rectify the mistakes and try to make the system work. It's also worth noting that sophisticated engineering can work. Here we have flushing sediment basins at Wadi Laba, weir and intake on the right side, big basins which flush back to the river down here. But it's all very expensive. Here's a photo of the actual basins, lots of concrete there. It's finally worth reminding you that increasing or changing the engineering interventions in these spate schemes may not create more water. We may just be moving around the water by giving more to the upstream and less to the downstream, unless the present situation means that water is passing through the area does not benefit others further downstream as eventually passing to the sea, then there's a justification for engineering interventions to reduce the losses to the sea. So, key conclusions. Firstly, learn from the successes and failures encountered elsewhere, which I've touched on a few here. Understand what may not work and why it may not work. However, also remember that what may not work in one place may work somewhere else, or vice versa, if circumstances are different. That is the end.